Okay, now today we'll start with another type of tree which is called as the height balance tree. Now this height balance tree is an important concept because you know that the complexity of a binary search tree will be an order of log n to order of n. But what I don't want the algorithm to go to order of n, because if it will go to the order of n, it will not be a very good algorithm. Therefore, in order to make sure that it is not an order of n algorithm, we are going to convert the algorithm in such a way that the tree algorithm always gives a complexity of log n. That means the word which is said over here is that it is height balanced. The height balance means that this tree will never become a skew tree, and every time the tree will be an height balance tree. Now, this is also called as an AVL tree. It is also called an AVL tree because it was invented by Adelson, Velsky, and Landis. They are the people who made this AVL tree: Adelson, Velsky, and Landis. Therefore, this is by their name we call it an AVL tree. Also, the height balance tree is general name. Now, what is the meaning? Now, this concept is little difficult. Therefore, you have to try to understand it very well. That how you are going to make the AVL tree. Now, the problem with AVL tree is that if you make one wrong somewhere, the tree will become all wrong, and therefore you have to make it very carefully how to go with that. Now, suppose I have a tree like this. Suppose some number for t. Obviously, the time to search will be an order of n. If it goes to say like this, the time complexity will be order of n. Now, suppose by some method I convert it into suppose like this. Obviously, this will be less than order of n. Therefore, this will be less than order of n. It will be, the complexity will be less than order of n. For example, I have one more number. For example, let us take 5. And I make this like this. Now the complexity for this two are the same, because it is also going to have, the height is going to be 3, the height of this also going to be 3. Now our aim is that I should always try to make the tree as height balanced. That means when I am going to make a tree, I will make it as a height balanced tree. Now that means these are height balanced trees. Even this is height balance tree. This is height balance tree. And therefore, the question is, what is the property of a height balance tree? Now, the property is very simple. Once you are going to make a tree, you have to make sure that how you can call a tree as height balance. Now, the property Now the property says that all nodes will have a balance factor equal to 0 or 1 or minus 1. Any tree where all nodes is having balance factor of 0, 1 or minus 1 will be called an avial tree. Now obviously the word which is important is the balance factor. So balance factor is defined as height of left subtree minus height of right subtree, and this should hold for all the nodes. This should hold for all the nodes. If any of the node violates this property, it will not be called an avial tree. That means the height of the left subtree minus height of the right subtree is equal to 0 or 1 or minus 1. Now if I take a modulus, obviously it will be 0 or 1. Therefore you might take a mod over here. In that case, it will be either 0 or 1 because minus 1 will convert to plus 1 if you take a mod. Now, if I am going to take this into consideration, let us I take a tree like this. Suppose I take some binary search tree as this. Obviously, this is a binary search tree. Now, let us try to calculate the balance factor. If I start with the leaf node, this is having a balance factor is equal to 0 because there is no left, there is no right. Again, this is 0, this is 0, this is 0. All of them will be having a balance factor is equal to 0 because they don't have left subtree, they don't have right subtree. Now, let us take for this. This will be 1 minus 0 will be equal to 1. Height of left is 1, height of right is 0, therefore 1 minus 2. If you take with this one, it is 1 minus 2, it is equal to minus 1. Now you take that from there, the subtree is having 1, the right subtree is having 2. Why? Because you know it very well. It is like this. This is 1 and this is 2. Now you take for this one, it is 0, sorry, it is 1 minus 1 is equal to 0. You take for this 1, 2, 2 minus 0. You take for the root 1, 2, 3 minus 3. This is 3 minus 3. And therefore the balance factor of all the nodes has been calculated. Now you check, is it clear that how the balance factor is being calculated? You take that node and take the height of the left subtree. Now if I take the root, the height of the subtree will be like this. You have to take this one, this one, this one. Or you can also take this one, and you can also take this one, and this one. In both the cases, it will be 3. Then you take for the right subtree. The height will be this, this, and this. Therefore, it is 3. 3 minus 3 is 0. Now, if you take this, what you find over here is that this is okay, this is okay, this is okay, this is fine, this is fine, this is fine, this is fine, this is fine. But this is not correct because it is having a balance factor of equal to 2. It means that this is not an avial tree. It is not an avial tree. But it is a binary search tree. It's a binary search tree. You put the numbers over there, the nodes, and if it is a binary search tree, it will be called a binary search tree. Now, in that case, I might put a number. Suppose I might take 70 over here, say 60, 50, say 20, say 55. Now, this is this is a base tree, but not an avial tree, because one of the nodes violate the property of a avial tree. Now, if this would have been like this, if this would have been like this, now calculate the Bayes factor of 6C. It is 2 minus 1 now. Now, the modified one will be now 2 minus 1. Because the height of left is 2, the height of right is also 1. And now, this is okay. And now you can say that this is an avial tree. Okay, sorry. Correct, you are correct. Let's take it like this. Fine. Thank you. Okay. Otherwise, you would anything happen on the right hand side also will make no difference actually. But of course, it was not a binary search tree because 105 would have come on the right hand side. By that also, the concept will be same. Now, here what happens, if this would have been the tree, this is an avial tree. But I don't mean to say that you make a tree and then try to see to that it is an avial tree or not an avial tree. You are going to make a tree, and at that moment only it should become a avial tree. That means every time you are going to make a tree, it should be an avial tree only. Okay, that means I don't. This is totally not a correct way that I am going to test it. I don't need to test. What I will do is that I make a tree, and then at that point of time, whenever the tree does not become an avial, I will convert it into an avial tree. That means, as and when the nodes are coming, I will keep on making a binary search tree. And then when I find that it violates the property of a BST, sorry, it violates the property of an AVL, I convert it into an AVL. And by this method, every time the tree will become an AVL tree. Now let us try to take a problem and try to show you how to this AVL tree works upon. Now, let us take a question that I want to make an AVL tree like this. Okay, I have to make an inventory with 100, 90, 80, 120, 150 and 200. Let us take this only 6 numbers. Now let us start making a tree. Now what I am going to do is that I am going to make a tree with this. First of all, I write 100. This becomes the root. You don't have to do anything because it's an AVL tree, because the balance factor of 100 is 0. 0 minus 0 is 0. Then you insert 90, just like a BST. You insert 90, 90 will insert over here. And you find the balance factor. Now balance factor for this will be 0, this will be 1. Correct? All leaf nodes will have a balance factor 0. 100 will be 1 minus 0 is 1. Then I add 80. Once I do 80, once I attach 80, now the balance factor will change now. Of course, the balance factor will be 0, 1 and 2. Because for 100, left subtree is 2, right subtree is 0, therefore this is 2. Therefore it will be 2 minus 0 will be 2, 1 minus 0 will be 1, and 0 minus 0 will be 0. Now at this point, it is a binary search tree, but not an AVL tree. Now it is not an AVL tree. And that means you have to convert it into an AVL tree. Now at this point, what you do is that convert this tree to AVL. Now, how to do this? Try to understand it very well, how I am going to convert it. Now, once I get this tree, what I do is that I calculate the balance factor. Now, the balance factor what you got is perfectly correct, and this was the balance factor which is calculated by you. Now, the node which has the balance factor equal to 2 or minus 2 will become the node which is called the pivot node. That means this node will the node which will become the pivot. This node will be the pivot node, because the node which is having a balance factor equal to 2 or minus 2 will be a pivot node. Now in this case, you find that there is only one node which having balance factor 2. Therefore, obviously that will become a pivot. But in some other cases, you will see that there could be 2 or more nodes also, which might become equal to having a balance factor of 2. There will be 2. There can be 2 nodes also, which is having a balance factor equal to 2 or minus 2. Now, at that moment, what you have to do is that for that one, you have to take that node which is nearest to the node where you have inserted. And therefore, you have to only do at the place where you find that that node is the nearest to the node where you attached. Now let us try to understand this and how I am going to convert it. Now I am going to take the case 1. Now the case 1 is a case which is called as the allele rotation. The allele stands for left-left. It is called the left-left rotation. Left-left rotation means, now try to understand why I call it allele. Unbalance unbalance occurs due to insertion in the left subtree of the left top pivot. Now understand this statement very well. Unbalance occurs due to insertion in the left subtree of the left of pivot. Now, what is the meaning? Unbalance is occurring due to insertion in the left subtree of the left of pivot. What is left of pivot? It is, come on, write on that. What is the left of pivot? Obviously, the left of pivot is 90. And you are going to insert in the left subtree of the 90. That means you are inserting in the left of 90. Therefore, if you are inserting 80, this becomes an LL rotation. And why this LL has come? Because of this particular L over here, and because of this L over here. And this 2 LL makes left rotation. This 2 LL makes left rotation. That means unbalance occurs due to insertion of in the left subtree of the left of pivot. The left subtree is, this is left subtree. And that means, but how did you come to left? 90 is left of pivot. Now this is okay. That means unbalance is occurring due to insertion in the left subtree of the left of pivot. Now, just try to make sure that if the insertion would have been here, now if the insertion would have been at this place, suppose the insertion would have been at 95. Now also you find that and it should not have been there. Suppose this would not have been there. That means also it will not be an AVL tree, because 90 will be having a bias factor of -1. 0 minus 1 is -1. Or you can say mod, it is also having a 1. Pivot will be same, but unbalance occurs due to insertion in the left, not in the left subtree, but in the right subtree. But this left is violated because left of pivot is 90, is okay, fine. But insertion is not being done in the left subtree, but is done in the right subtree. That means it is done in the right subtree, and that means you are going to insert in the right subtree. In the right subtree. Now, in that case, previously this was the left subtree. This was the left subtree. That means when I talk about this one, I am going to make sure now unbalance occurs due to insertion in the left subtree of the left pivot. Now this is the left subtree. And this is the left pivot. And if I have inside 95, it had been a right subtree. That means you cannot implement a LL rotation over there. Now, once you are having this type of thing, you apply a LL rotation. And in LL rotation, what you are going to do, from this part, you perform a clockwise rotation. You perform a clockwise rotation. A clockwise rotation is from the pivot. That means you take the pivot and perform a clockwise rotation. When you are going to perform a clockwise rotation, Now this tree will now translate to like this. Like this. What will happen? You take 90 as the pivot, and what you are going to do is that you are going to rotate the tree from taking 100 as the pivot, and if you rotate the tree, 90 will come up, 80 will also come up, and 100 will go down, because you are going to rotate like this. You are going to rotate like this, and once you are going to rotate like this, you will be getting this type of tree, which is an avial tree. And now this is an avial tree. This is not avial. Fine. Now what I'm going to do is that I take other numbers. Now the other numbers are 120, 150 and 200. 120, 150 and 200. Now insert 120. Now when I'm going to insert 120, you know that once I'm going to insert 120, you are going to insert at this place. See, I'm inserting just like a binary search tree. I'm not doing any other thing. I'm just inserting as a normal binary search tree. Now you calculate the balance factor. Obviously, this tree is balanced because 100 is having a balance factor is equal to -1. This is also having a balance factor of -1. 80, 120 will always be 0 because those are leaf nodes. There is no need to calculate for leaf nodes also. Now, in that case, you are going to calculate by this method. You will be having this one. Now, I insert 150 now. I insert 150. And again calculate the balance factor. Obviously, this will become -1. This will become -2. And this will become again. Why? Because for 100 is 0 minus 2. For 90 it is 1 minus 3. Therefore this has come because of 1 minus 3. This has come because 0 minus 2. This has come because of 0 minus 1. Correct? And now you will get this tree. Now here you find that there are two pivots. There are two pivots. One is 100, another is 90. And it is a case where you will find that there could be more than one pivot also. But I don't mean to say there will be more than one pivot. There are two nodes which are having a balance factor of 2 or minus 2. But the pivot will be the one which is nearer to 150. The pivot will be the one which is near to 150. Now in that case, it means that this will become the pivot. Why? Because 100 is near to 150 than 90. The distance from 100 to 150 is 2. The distance from 90 to 150 is 3. Therefore, in that case, 100 is nearer to 150. Therefore, 100 becomes the pivot and 90 does not become the pivot. Is it clear to you that how I am taking the pivot? The pivot element is the element which is having a balance factor -2 or +2, depending on the case, and you are inserting, and that is the nearer to the node which has been inserted right now. The node which has been inserted is 150. Therefore, 100 is nearer to 150. Therefore, 100 becomes the pivot. Now, can I apply LL rotation in this one? No, I can't apply because it is neither the left subtree nor the left of pivot. Now, in that case, this case is a mirror rotation of LL. Now, what I am going to do is that I am going to do the other rotation, the RR rotation. It says that and you see this R over here and this R over here makes this R rotation. That means unbalance occurs due to insertion in the right subtree of the right of pivot. Now, just to come to the back, this one, what is right of pivot? Is 120. You are inserting in the right subtree of 120, therefore this is RR rotation. Because this is right subtree. And this is right of pivot. (120) is right of pivot and 150 is the right of subtree. Now, any insertion done at 150 or below 150 will all be in the right subtree. Now, it means that if any insertion would have been done, say, below 150 also, that is all right subtree. Okay. Yeah, Shabuddin. Anything, what do you want to ask? Did you understand?
Sir, why you have taken nearest from 150? My question is this. Sir.
Why we have taken?
Nearest from 150.
No, what I am doing is that, did you understand why I took 100 as pivot? Because there are two nodes which are having a balance factor of -2. One is 100 and one is 90. But the node which is nearest to the new node will become the pivot. Since 100 is near to 90, 100 becomes the pivot. Now, the original tree was only having 90, 80, 100 and 120, and you have inserted this node right now. You have inserted this node right now. Now, in that case, insertion has been done in the right of pivot, in the right subtree of that node. That means, what is right of pivot? Is 120. Insertion is being done in the right subtree of 120, therefore it is an RR rotation. There it is an RR rotation. That means, if I had inserted at the left of 120, this was not an RR rotation. If insertion would have taken place in the left, for example, I might have inserted somewhere over here. I might have inserted, say, at this place, maybe 110. Instead of 150, I would have inserted 110. Now, this is also right of pivot is okay, but 110 is left subtree and not a right subtree of 120. Therefore, this rotation will not be an RR rotation. It will not be an RR rotation. That means you have to identify clearly where is LL, where is RR, or whatever the rotations are. Therefore, there are 4 rotations: LL, RR, LR, and RL. LR stands for left right, RL stands for right left, LL stands for left left, and RR stands for right right. Is it clear to you? Now, once I get this, you have to perform the rotation which is called, now you have to perform RR rotation. Now, RR rotation will take place by putting a right to right rotation. Therefore, what I am going to do is that I am going to do, just I'll do it over here. And this is the pivot. I will do an anti-clockwise rotation, taking 100 as the pivot. Now this is anti-clockwise. And once I do this, 120 will rise, 150 will also rise up, 100 will go down from that point. Now in that case, now this will be the resulting tree. Now this will convert to this. Why? Because 120 moved up, 150 also moved up, and 100 comes down from taking 100 as pivot. That means you have to rotate at this point, and you find that this is a real tree. This is an avial tree. Is it clear that this is an avial tree, where because all the nodes are having a balance factor is equal to 1 or minus 1 or 0. Okay. Now that means we have covered 2 rotations, LL and LR. Now let me try to show you that why. Suppose I take a tree like this. Now tell me, is it an avial tree? Is it an avial tree?
Yes, sir.
Yes, it's an avial tree. Fine. Now, what I'm going to do is that I am going to add a node at this place. Now this tree. Where the unbalance occurs? Obviously, it is not an avial tree. Now let me try to put some numbers. Suppose I put 100, then 120, 110, 140, 130, say 160, suppose 180. And maybe putting some 70 over here, 60 and 80. Fine. Now where does the unbalance occurs? It occurs at not at 160, not at 140, but unbalance occurs over here. Obviously, it also -2 also 100 also become -2, because what is the balance factor of 100? 2 minus 4. It is 2 minus 4. Left subtree is 2, right subtree is 4. But 120 is having balance factor 2 because 1 minus 3, and 120 becomes a balance factor, becomes the pivot. Now, what is right of pivot? Is 140. Now I am inserting in the right subtree of 140. In the right subtree of 140. Now, in this case, this was the right subtree. Inserting in the right subtree of 140. And this is the right of pivot. Now here I am not inserting at 160, I am inserting down the line. It could be inserted at this place, or it is inserted at this place. Now let us take an example. If I have inserted, suppose here I would have inserted 150. Now try to understand it very well. I am inserting at, instead of inserting 180, I am inserting 150. Now, what type of rotation it is? Right of pivot is R. Is it in the right subtree of pivot? Is it in the right subtree of? Because RR says that unbalance occurs due to insertion in the right subtree of the right of the pivot. Right pivot of the pivot is okay. Right subtree is 160. Therefore, in this case, either you insert 150 or 180, both are RR only. Because you are inserting in the right subtree of 140. You are inserting in the right subtree of 160. That means right of pivot is 140. Right subtree of 140 is 160. You are inserting either 150 or 180. Both becomes right in the right subtree. But if I inserted at 130, this would not be an RR. Are you getting it? That why I say both are RR? Because you are inserting at this position. And 160 is the right subtree of 140. 160 is the right subtree of 140. Therefore, either you insert in the right of 160 or in the left of 160, it is same. But if I insert in the at 130, it will not be same. Now, let us try to understand how this will work upon. Now, this is the case. Now, rotation will take place at this place. Now, this case has to be understood in that context. Now, how it will be now? Now, this will be same. Now, you understand one thing, that if I am going to do any rotation in the right subtree, left will not have any effect. That means 170, 60, 80 will be as it is. The only difference, whatever will happen, will be only having in the right subtree 120 and below that. Nothing will happen above 120. If I have drawn this to show you that 100, 170, 60, 80 will remain unaffected. Now, if I am going to perform RR, 140 will rise up and will become the root. Now, what will happen? 140 will become the root. And 160 and 180 will rise up. and you will find that they are, and over here, when I rise over there, 120 will go down and 110 will become here. But you find one thing, that where is the space for 130? Now try to understand, when I do this, 140 rises upward. When you rise 140 upward, 160 will also rise, 180 will also rise, and 120 will come down, and 110 will come further down, because you are rotating, taking 120 as the pivot. Now once you are doing an anti-clockwise rotation, 140 will go up, 160 will go up, 180 will go up, 120 will go down, and 110 will go down. But there is no space for 130, because 130 was in the left of 140, which is now occupied by 120. But this means that whenever such type of rotation takes place, there is one space which is now remains vacant. Now what remains vacant is there is no right of 120. Why? Because once you do a RF rotation, 120 comes down, and the right of 120 is now free, is vacant, and that means you put 130 over here. Why did I put 130 over there? Because the rule says that the node which does not have the place will be put at that place which has become right now vacant. Now 120 of right was already occupied by 140, but once 120 came down, right of 120 is now free. It is now vacant, and that means this 120 will be attached to the right of 120, and now this is a AVL point. Okay, now by this method, 5 minutes back. Now by this method, you can very well try to make sure that this tree converts into an AVL tree. Now anything which could have been here, the whole subtree you will put at the right of 120. Either there is one node or two nodes or three nodes or n number of nodes. This entire box what I made has to be copied as it is at 120. And this is how you are going to make an AVL tree.
Sir, I have a doubt.
Yeah.
Sir, what if we just move 160 upwards in place of 140, and then 140 comes to the left of 160 followed by 130 and the right side remains at 180?
No, that could have been there, but we are following an algorithm for that. Actually, we are not doing it random. The rule says that you have to perform rotation from pivot and not at there. Now, in that case, you might say that I can put 160 at top and then 140 at bottom, but that is not the way, because it might solve this question, but other question will not be solved by that method. You might be able to solve this question by putting 160 at the top, putting 140 on the left and 130 at left, but that is just a possibility in this question. If I take a general case, it will not work like that. And I will show you that what you are trying to say may work over here, but may not work at all times.
Yes, sir, it depends on the tree itself, the values.
Because at some point of time, the tree shape might be very, very different. And there could be many nodes at the bottom. Okay, then stop at this point. We'll continue on the next class with this. I will try to do a lot of problem, because this is a little tricky chapter. And once you make anywhere you make something wrong, this will overall make the whole tree wrong. Therefore, you have to be very careful that at every point when I am going to insert a node, I will be able to to do that. Now, as far as what you are asking is that how to manage these pointers, it is not that difficult. The code for this is not that difficult. It's a small code. Hardly around 40-50 lines code will work upon this.